Yes, good morning, students. So I think we have came to an end of what we call it a discussion about linked list. So today we are going to see about the last part of linked list, which is left. Okay, and once we complete that, we are going to discuss about going forward. So yes, okay, let's start our discussion. Okay, just we'll wait for few minutes. Okay, some participants are joining. Then I have to tell them, I have to give a message to them. So wait for a moment. Yes, all those participants who have, all those students who have joined now. Okay, please next time I am not going to welcome you. You are joining exactly at 10:10. This is not good. Please try to join early. Yes. So good morning, students. So we have almost reached at the end of discussion of our linked list, and we have seen all different kinds of linked list. Starting from we started with a single linked list, then we moved on to circular linked list, then we moved on to doubly linked list, and then finally we saw about header linked list also. Also, we have discussed about the algorithms with respect to all these different kinds of linked list. As in, we have seen how insertion is possible in all of this linked list, except of course header linked list. Then we have seen about traversal operation. Then we have seen about deletion operation. We have also seen about searching operation. When we talked about single linked list, we even have seen operations like copying a linked list, merging a linked list, splitting a linked list, and so on. That's how we have almost understood these data structure to a quite a good extent. And our today's discussion is basically going to focus on what are the applications of linked list. So basically, there are three applications of linked list which we see. Linked lists are used to represent polynomials. Now, polynomials is nothing but a mathematical concept which you're already aware of. But then, when we want to actually represent them, so to write it on a piece of a paper, a polynomial to write it on a piece of a paper is quite easy. But when we want to represent that polynomial in actually a machine, okay, how do we do that? Or in, let's say, in any of our programming language, wherever we have, let's say, maybe in any application wherein we are going to use this polynomials to add it or do certain mathematical operations. So linked list is quite used there. Linked list is also going to is used for representing sparse matrices. Now, what is the concept of sparse matrices? I think we have already seen when we have understood our first data structure, that is array, and we have also seen that what is a sparse array or what a sparse matrices look like. So yeah, definitely, we'll have a quick recall of it today. And also we are going to see that how linked lists are going to be important for that. Then one another major application of linked list is that basically it is used to implement other data structures. Okay, the other data structures which we haven't seen till now. And there are two more concepts, okay, which we have to see, is that is so which are a bit different, that is de-allocation of memory. So we do have seen that we can make use of malloc to what we call it as allocate the memory. But then when we perform delete operations at many of our algorithms, we have written something like delete begin, delete temp, or something like that. So how basically when we say delete, basically we want that the memory of it should not be now there. So how can we achieve a state wherein or how what function basically we can write which is very similar to malloc, which actually will help you to deallocate the memory also. And then one of the operation of single linked list which was remaining, that is reversing the single linked list. So that also we are going to see today. Fine. So let's start with the application of linked list. Okay, so the very first application of linked list. So yeah, as we already discussed, that linked list is basically used in different kinds of applications. But then some of the major applications, okay, wherein linked list is used more is to represent polynomials, represent sparse matrices, to implement the other data structures. Fine. So let's start with the very first application. Now, the first application is representation of polynomials. Fine. To represent a polynomial, first of all, I should know what is a polynomial, right? Okay. So a polynomial is an expression in which variable x is in the form of ax plus bx plus, and of course, there can be some raised to power n also plus jx plus k, where a, B, C, K fall in the category of real numbers, and N is a non-negative integer, which is called the degree of polynomial. Okay, so basically, N raised to will be there, so it can be A x raised to N and B x raised to N, something like that. Okay, so wherein your N is known as degree of polynomial, and your A, B, and C are known as just we can say coefficients or something like that. So yeah, definitely we are going to take an example and understand, but I think we definitely know what a polynomial looks like. Okay, so let's see, if I'm writing 4x square plus 3x plus 2, so that is nothing but what I call it as polynomial. And we also have seen that how we can perform addition of polynomials or deletion of polynomials likewise. So point over here is that how linked list is going to actually help us to represent this polynomials. So that is more important for us to understand. So fine, this was about polynomial. Now we'll see how linked list is actually helping us. So whenever we want to represent polynomial, we have to understand that what is the polynomial consisting of. So an essential characteristic of the polynomial is that each term in the polynomial expression consists of two parts. One is the coefficient, other is the exponent. So here we have taken example like 10x square plus 26x. Now, in case of 10x square, we know that the raised to power is 2 for x, and whereas in case of 26x, we have seen that the raised to power x is 1. So here what we say is that 10 and 26 are nothing but your coefficients, and 2 because x raised to 2 over here. So 2 and x raised to 1 over here. So 2 and 1 are its exponential value. Okay. So this is an example of polynomial. And yeah, I think we are using polynomial since quite amount of time, maybe for since our schooling days. So we definitely know that what a polynomial looks like. So this was an example of a polynomial. Now let us see that how linked list is actually helping us to represent it. Fine. Uh, the linked list can be used to represent a polynomial of any degree. Simply the information field is changed according to the number of variables used in the polynomial. If a single variable is used in the polynomial, the information of the node contains two parts, one for the coefficient of the variable and one for the degree of the variable. So basically now your node is going to contain, till now we have seen that our node is going to contain a data part, and then there was a next. Or also we have seen a node wherein we have a data and where we have next and previous, and also we have seen a kind of a node which is known as header node, which contains certain information. But basically what we have seen till now is that there is only one data part, and there can be either one place for memory address or two place for memory addresses. Okay, but now when you are talking about polynomial, basically you need two part. Okay, one part is to um, mention the coefficient of the variable, and other part to also mention the degree of the variable. And of course you will definitely need a next pointer which can help you to connect to your next part of the polynomial, because a polynomial is not going to be a single expression, right? Okay, so that's what we saw over here, is that if we talk about 10x square plus 26x, okay, then this is going to be one and this is going to be second. So that's why basically we will need, okay, definitely a connecting node also. Okay, so taking an example, so we have taken an example of a polynomial like 3x cube minus 4x square plus 2x minus 9. Okay, so now when we say the line something like that, either there can be one variable or two variable. Okay, so majorly here we are talking about that the variable is one, which means everywhere where you see in the polynomial we are making use of x only. Yeah, definitely, there can be polynomials wherein one part will have a different variable, let's say 3x square plus 4y or something like that. In that case, we have to make two different polynomials. But let's say, or we can say in that case we have to make two different linked lists. But let's say in this case where you have x only throughout, okay, you can make use of one linked list only and you can represent. So now very important point comes over here is how we are going to represent it using a linked list. Okay, so now, as I already told you, instead of one data part, there will be two data parts. Okay, so that's what we see a difference over here. So every node in the linked list is now having two data parts. And of course, there is a next pointer which is helping us to connect, to the next part of your polynomial. So see, if I just if I just slice this polynomial or break down this polynomial, I can see that the first part of the polynomial is 3x cube. Then I see the next part of my polynomial is minus 4x square. Then I see the next part of my polynomial is plus 2x. And then I see the next part of my polynomial is minus 9. Okay, so this is very important to understand. The breaking is because every breakup is going to actually create your node. So let's talk about the first breakup. So the first breakup says 3x cube. Okay, so as we already told that how we are going to represent. So one, we are going to make use for the coefficient. Okay, so if we talk about 3x cube, what is the coefficient? 3. So 3 we have kept over here. And next is the degree of the variable. Our variable is x, and what is the degree of it? Okay, 3. So that's why what we see is that your first node is containing 3 3, and it is root, or begin or head, whatever word we can use, but we are most familiar with begin, so we can definitely mention begin over here. Fine. Now this is a next field because it is going to try to connect to the next part. Now what is next part? Minus 4x squared. So what is the coefficient? Minus 4. And what is the degree of the variable? 2. Going forward, we have to connect the next part. The next part is 2x. What is the coefficient? 2. What is the degree of variable? Because it is x, so okay, it is only x, so that therefore the exponent will be 1 only. Going forward, what is the coefficient? Minus 9. And now basically it does not have any variable attached to it. Okay, the degree of coefficient will come 0. So this is how you can make use of linked list. And yeah, because the polynomial is terminating over here, the next part of the last one, what we see is when you denote it by cross, it is nothing but trying to tell you that it is a null point. It is null over there. So this is how basically you make use of linked list to represent the polynomials. Okay, so if we go ahead, okay, when we talk about representation of polynomials as an application with linked list, we do have to explain what is a polynomial. Okay, so that is the first thing. And we do have to understand that what a polynomial consists of. So polynomial consists of an coefficient and an exponent. We do have to understand that what a node will contain when you talk about representation of polynomials. So we talk that if we are going to make use of linked list, then there will be two major parts which will be act as in data part into our node, that is one for the coefficient and one for the degree, and definitely your third part is going to be your next. And then we take an example of any polynomial. Okay, and then we try to represent it diagrammatically with the help of a linked list. Okay, so this is the very first application, students. Okay, which basically you can make use of linked list over here. So that is representation of polynomials. Fine. Now let's go to the second application for linked list. So the second application is represent of sparse matrices. So I think we very well now know that what is a sparse matrices. Okay, so when we are taking a two-dimensional array, so basically first of all it has to be very clear that whenever you are talking about matrices, you are talking about a two-dimensional array. A two-dimensional array can have any number of rows and columns, and we'll have certain, of course, values with respect to rows and columns. But now when in this two-dimensional matrices you have more number of zero values than non-zero values, which means when you see the matrices, it looks like that there are many places wherein you just have value 0 0 0 0, and there are very less places when basically you have non-zero values. Then those kind of matrices are known as sparse matrices. And we also have seen that how basically we can actually store these sparse matrices. So when we have seen the concept of sparse matrices in arrays, we have seen that how we can actually store these sparse matrices, okay, or how we can represent these sparse matrices. So we have seen we can either use method of linearization, and we have also seen that we can use method of vectorization. And then the third method that we are going to see is today is using linked list. So basically, whenever you want to store sparse matrices, there are three representations available. Either you can make use of method of linearization, which means you can make an use of another array itself, and you can simply extract the non-zero values from a sparse matrix and put it into a 1D array. The second thing is that you can make use of vector. So vector is going to make use of rows and columns, and the wherein basically you're going to have non-zero values. And today the third kind of representation that we are going to see is how we can actually make use of linked list to store the sparse matrix. So a linked list may be used to store a sparse matrix by representing each non-zero value as node and linking this node in a specific way so that it represents the position in the original array. Okay, so now this is very important, because when we are going to make use of a sparse matrix, okay, so let's say if we use the first method, that is method of linearization, we just get the values, but we never are able to understand that where in the matrix they are stored. Whereas in either method of linear vectorization or linked list, you can also store the position of its we can see either row and column in which they are specifically located. Okay, so now the representation of sparse matrix with the help of linked list is very similar to what we have seen in the method of vectorization. But over here, definitely one more part will be there, that is the next node. Okay, so what we see over here, that even if we are going to make use of linked list, we have row, column and value. Okay, which means whatever non-zero value will be there into your sparse matrix, you are going to represent it into linked list using in which row it is located, in which column it is located, and what is the exactly value. And thereby it is actually going to help us to connect the next node. So each node in the linked list has now 4 fields. Okay, so now what we see that when we talk about sparse matrices, there are 4 fields into the linked list. When we talked about just when we talked about polynomials, we saw that there are 2 fields and a next node. And here what we see now, that there are 3 fields and a next node. Definitely when a linked list is there, you have to consider next node, because that's what the linked list is just trying to tell you, that it has to connect to the next node. Okay, so that is something which is extremely important. But now over here, with next node, you have the values of row, column, and the particular value of that non-zero element associated with it. So yeah, we can just take an example and try to understand. Now first of all, this is an example of a sparse matrix. Okay, why? Because what we see is that there are many zero values and there are very few values which are non-zero. So if I talk about first row, in that 3 and 4 is there, rest of the 3 values are 0. Over here also 5 and 7 is there, rest of the values are 0. In the third row, everything is almost 0 only, there is no non-zero value. And in the fourth row, what we see, again there are 2 values which are non-zero and rest of the values are 0. So now how we are going to represent it? So this is just a kind of a structure given to us, that basically we are going to make use of address of next node, column and column index, and the value. Okay, so we have created a row list. Okay, and now row list, every row is actually pointing a node like this. Okay, so now the first part, that is the row, is actually you have created into what you call it as a separate linked list, wherein there is only row index which is mentioned, and there is a next field associated with it. And next is actually going to connect all the nodes in the row which are going to have non-zero values with their corresponding column values also. So now this is the row index 1. Okay, it is actually pointing to row index 3, and what is there at row index 3? A value which is 3. Then this node has to actually point another node, okay, into the same row which is again having a non-zero value. So now another node is created, and the column is 5, because if we talk about 1 2 3 4 5, okay, fifth column, and what is the value? 4. And now there is nothing more, so it has basically stopped over here. And now we talk about the second row. Okay, so second row, where is the non-zero value first coming? In the third column. What is the value? 5th. Then in the fourth column, what is the value? 7. Fine. Then what about the third row? In third row, actually all the values are 0 only. So basically it is pointing to null, telling that there is nothing into this row which is non-zero. And then we go to the fourth row. Then what we see is that second column values 2, and the third column with value 6. So this is how basically, you are going to make use of sparse a linked list. Okay, so to basically mention a sparse matrices. Okay, so this is the second we can say application of linked list, okay, to represent the sparse matrices. Okay, we'll once again understand it. So first of all, what is a sparse matrix? Okay, a sparse matrix is something which is going to have more number of zero values than the non-zero values. Okay, so here when we have taken an example, so we see it is a 4 by 4 matrix. Okay, if it is a 4 by 4 matrix, basically there are 16 elements which it stores, and from 16 elements, how many elements are non-zero? So only 1 2 3 4 5 and 6, only 6 elements are non-zero, which means total 10 elements are there into this matrix, okay, which are holding the value 0. So this is definitely an example of a sparse matrix, because we are having more zero values than non-zero values. Fine. Now, as we have already discussed this concept of sparse matrices, and we also have discussed that these sparse matrices can be stored even with the help of a 1D array, or even with the help of a method of factorization. And there is third different way, okay, which can be also used to store these sparse matrices, that is making use of linked list. Okay. Now, whenever we are making use of linked list, what basically we are going to use? So we are going to make use of, first of all, the row index. Okay. So we are going to make use of all the rows. Okay. Now, one thing is that we might not be sure that in which row there will be a non-zero element, and in which row the non-zero element is not there. So for a safer side, we consider all the row indexes, and then if there is none of the element into that row which is non-zero, so like an example of the third row over here, we can just point it to null, just telling that there is no non-zero element over here. Okay. So yeah, that is one thing. And it will have row, column, value, and next node. Okay. And so we have seen an example of a sparse matrix. Okay, so yeah, definitely this is a sparse matrix. Why? Because now it is having actually non-zero values which are very less. And now let us understand that how we represent it. So we have given row number 1, and it will point to the very first value which is non-zero, so that is 3. At what column index it is located? At column index 3. So it is 3 3. Then it is pointing to the next node, maybe the next non-zero value into this particular row. So the next non-zero value in this row is 4, and it is at located column index 5. Then if we talk about the second row, the first non-zero value is 5, which is located at column number 3. The second non-zero value is 7, which is located at column number 4. In the third row, all the values are 0, which means there are no non-zero values. In the fourth row, the first non-zero value is 2, and it is located at column number 2. And the second non-zero value is 6, which is located at the column number 3. So this is how your sparse matrix basically is going to get converted into a structure like this now when we are going to make use of linked list. Okay. So yeah, this is about representation of sparse matrices, which was about the second application of linked list. Okay. So we have already seen in our beginning session today is that we are going to make use of linked list. Definitely, there are n number of applications wherein linked lists are going to be used. Okay, but yeah, we are going to see some very important applications which are used on and off. Okay. So they were to represent polynomials, to represent sparse matrices. Okay, so we have seen that how actually linked lists help in representing polynomials, and even how linked lists help in representing sparse matrices. So now the third application is to implement other data structures. So now when you talk about other data structures, so which other data structures you are trying to talk about? Because there is a one data structure that we have already discussed, that is array. Now array itself has its own way of representing itself, so definitely we are not going to make use of linked list to represent array, because they both are completely different. Okay, and we have seen that how array basically makes use of contiguous memory locations to store its elements, and in linked list it is way different in the sense that linked list actually allocates the memory dynamically, and then it just connects the node with each other. So that is what we have seen. But now there are some, so if basically I have to talk about array and linked list, then array and linked list are what is I'm going to call is are the basic data structures, right? Okay, and rest of the data structures, okay, that we are about to see, which are stack, queue, tree, and graph. Okay, so these are the another four data structures which are at times also known as derived kind of data structures, which means you can make use of array to represent stack, queue, tree, graph, or even you can make use of linked list to represent all these data structures or to implement all these data structures. So either array or linked list can be used to make all the data structures, okay, which we are going to understand, that is stack, queue, tree, and graph. So thereby the third application of the linked list is to implement other data structures. And whenever when we have also seen about applications of array, also we have discussed over there that how arrays are also useful to implement these data structures. So that is the third application of linked list. So again, students, okay, summarizing about the applications of linked list, there are three applications of linked list. First is to represent polynomials. Second is to represent sparse matrices, and the third application is to implement some another data structures. Okay, so that was about applications of linked list. Now the next concept that we have to see is about de-allocation of memory. Okay, so as I have already discussed with you that we do make use of malloc, and we have seen making use of malloc to allocate memory to a particular node. Okay, so we know that we used to write a code which is something like malloc size of then struct node, and then typecast it to node, because we want to dynamically basically allocate memory when we talk about linked list. But this is so whenever we there are basically two operations. The first operation is insertion operation. So whenever you want to insert, you want to try to say that I want to create a new node, and fix it somewhere into the linked list, either fix it at the beginning of a linked list or at the end of the linked list, or maybe somewhere at a particular position into the linked list. But whenever you say that you want to perform an insert operation, which means you are deliberately trying to tell is that my need is to create a new node. And whenever your need is to create a new node, basically you are talking about you want to allocate a memory to a node, and therefore basically the memory function which you're going to make use of is malloc. Okay, now so there are different memory functions for allocation of memory. Okay, that is calloc, malloc, and realloc. Okay, we have seen that how basically we make use of malloc. But now we do also have seen that there can be operations wherein you are going to delete a particular node. Again, either you're going to delete a node from the beginning or at the end, or somewhere from the between. But what if, okay, what if the memory with respect to that node does not get deleted? Okay, in that case, okay, the use of the linked list is not sufficient. Okay, or the use of the linked list is actually going to uh, 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 not help us, because when we say that we are going to make use of linked list, we definitely want that allocation as well as the allocation should happen dynamically. Okay, which means if I am saying that I want to delete a node, that has to be permanently deleted from the memory, which means again that the memory which is allocated by that node should not be there. Okay, so if we want to do that, we can make use of a function which is known as free, and we have to just pass the pointer of a position of a node, or maybe of a place from where we want to delete a particular node. So whenever we have seen the deletion algorithms, and we have written delete temp, because temp may either be pointing to beginning or end or something, and we want to actually delete that node. So whenever we write delete temp, okay, basically in terms of programming, we are going to write free temp. Okay, and when we are going to write free temp, basically it's going to remove the memory of a place to which temp is pointing right now. So whenever you write free and pass a pointer to it, the pointer is going to point to some memory address. So let's say your pointer is pointing to a memory address which is, let's say, 5004 5004. And when you say a free pointer, okay, so whatever is located at memory address 5004 is going to is going to get deallocated, or it's going to be erased from the memory or something like that. Okay, but that is not the case with array, students. Okay, when you say deleting in arrays, okay, the memory location of the array is not fixed. If you have declared an array of size 50, throughout the program it is going to remain as size 50 only. Okay, the memory will stay as it is. Yeah, it is possible that you can keep on changing the elements over there, which means if you say you have deleted 5 into an array, then instead of 5 you can put 10 over here or 15 over here, but the memory of that 5 is never ever going to be deleted. Whereas if we talk about linked list, then the memory with respect to it is definitely going to get deleted. Okay, so that is about deallocation. So one thing we have to definitely understand and remember is that if you want to allocate memory, we can make use of malloc, and if you want to delete the memory, or if you want to free the memory, we are going to make use of free function. Okay, so both the functions are available into our C library. Fine. Now we are going to understand about a concept which is known as reversing and linked list. Okay, so let me first explain you, then we are going to see this basically kind of a GIF again. So when you say reversing single linked list, okay, so we do have seen an algorithm wherein we have understood about how we can actually reverse a doubly linked list, and or we have seen that how we can traverse a doubly linked list from beginning to end, as well as from end to beginning. Because in doubly linked list we were actually making use of previous pointers, and whenever we make use of previous pointers, it becomes extremely easy for us to navigate into the reverse direction also. But what about search single linked list? Okay, single linked list actually does not make use of the previous pointers. So how we are going to make a concept like reversing a single linked list when you are talking about when you're going to talking about a single linked list wherein you just have a next pointer. So now what we do is that definitely we'll start with head. Okay, and we'll start with a current node. Okay, and probably our current is going to point to the head. And then because in single linked list we only have next, but for making it because we have to make it reverse, we have to understand what is previous to it. And that's why what we do is we also make use of previous. Okay, and then see how we can achieve reversing a linked list. Okay, so let us try to understand. Okay, let us try to understand what has happened is previous is pointing to null, and so was next, and next has moved ahead, and now previous is pointing to this, next has again moved ahead. Okay, and current is pointing to this, now previous is pointing to current, next has again moved ahead, current is pointing to next. Okay, and previous was pointing to this, again current has taken this place, and now previous is pointing to this. So what every time, okay, we have seen is that that a next is there, that first of all your previous and next were pointing at a particular place, your head and current were pointing to a particular place. You have shifted next one moment one ahead, and you have shifted current, and now you have pointed your previous to current, and you do this journey till the end. You reach the last node, and while doing this, okay, whatever the previous was there, or whatever the current was there is getting assigned to previous, and thereby the links are getting changed. And finally what you did is when you reach at the last node, okay, you have actually given your reference of the head pointer over there. And so by doing this, okay, what exactly has happened, at least wherein there was a connectivity wherein you were having 1 2 and 3, has actually now changed to 3 2 and 1. Okay, so this is how. Okay, so you can spend some minutes and understand that how basically this is working. Yeah, so the algorithm looks like while current is not equals to null, next should be equals to current of next. So now next is moving one step ahead, and current of next is actually pointing to previous. Previous is equals to current, current is becoming next. Okay, this happens again and again till the till the time your current is actually not reaching the null value, and once it has reached the null value, the last is going to change its reference to the head pointer, and now your head is going to now basically point at the last node which is there into your linked list. So this is how a reversing happens when we talk about a singly linked list. Fine. Yes. So yeah, now if we sum up our today's session, then what we have seen is that we have seen about applications of linked list. Okay, so this was the major thing that we have seen today. That we have seen that how we can make use of linked list to represent polynomials, to represent sparse matrices, and even to implement other data structures. So we have seen that when we want to represent polynomials, how two things are important, that is coefficient and degree of variable. Then we want to represent sparse matrices. Then what is it? Sparse matrice basically more zero values than non-zero values, and we make use of row, column, and the particular value to represent those non-zero values. So we have basically seen that how we maintain a row list, and then it points to all the column we can say numbers wherein we have non-zero values associated with it. And if there is a row in which there is no non-zero value, then it can have a null associated with it. Okay, so that's what we have seen. After that, we also have seen that how we can make use of free function to basically deallocate some memory. And we also have seen that how we can perform reversing of a singly linked list. Okay, so yes, students, that was there for today's session. Thank you all of you. Thank you.